In this video, we're going to be solving this problem. It reads, show that the minimum stopping distance for a car traveling at speed v is this, what I'm calling delta x min, or d min, minimum distance, equals the speed squared divided by 2 mu s times gravity. So it doesn't give us a lot of information. It just says, prove that this is right. Show us that you can derive the equation that we're giving you here. So here's what we're going to do. We're going to first start by sketching a picture of what's going on, and then we're going to make some reasonable assumptions that are going to allow us to get to this final equation. So let's go ahead and draw our picture. I'm going to imagine that this is a car and it's going to be driving along on a level road. So that's already one assumption you can name. It's just a flat road. So in physics, we cannot do any measurements or calculations without applying our own coordinate system. So I'm going to assume that right is the positive x direction and left is the negative x direction. So that means I'm going to say that this car is traveling with an initial speed v in the positive x direction, just because I choose to label it that way. Now, to help us organize our information even more, we're going to create a table of knowns and unknowns. And this is a way for us to take inventory of information we're given and what we're trying to solve for. So it looks like this. So this is our table of knowns and unknown values. And what we're going to do is that if we know a certain particular value, then we're going to write it under the known column. If we're trying to solve for something, then we're going to write it under the unknown column. So the question says, show that the minimum stopping distance. That means I'm looking for what I'm calling delta x min, the minimum stopping distance. Now, we need to pay careful attention to the sentence because it's going to give us a lot more information than it appears to give. So let's take a look. It says, show that the minimum stopping distance. Okay, think about what that means. Minimum stopping distance. That means the car is going to come to a stop. It's going to come to a rest at some time later. So what that means is that I can say that the speed horizontally at the very end, I call that final, is going to be equal to 0. So the final horizontal speed will be 0 because it is coming to a stop. Okay, so that's one big piece of information you need to take from reading that single sentence. Okay, here's another thing. Show that the minimum stopping distance for a car traveling at speed v. That means at the very beginning of this motion of when we open our eyes and we see this or visualize this scenario happening, at the very beginning, this car has an initial speed. So I can say that the horizontal speed at the very beginning initially is just equal to v, positive v in fact. Now here's another thing. In order for me to correctly be able to figure out how far this is going to go, this car must be slowing down, meaning that there must be a net force acting upon it. Because if there were not, then this car would simply go at the same speed v forever in a straight line if there is no net force acting on it. But because this car starts at speed v and it's coming to a stop, there must be a net force acting in the opposite direction of its motion. So I know that there's some net force acting this way on it, and that's going to be the direction of the acceleration. That's the only way for objects to come to a stop. And so it's something I need to figure out, but I'm going to try to find this horizontal acceleration. Now here's another thing. If there is no other outside contact force, that means the only object that is touching this car is the surface, which means that the force providing this acceleration is going to be due to friction. And so I'm going to need to find, so I know that the force of friction is going to be something that's going to be important to me. Now, for us to finally dig deeper into this, we're going to have to draw a free body diagram. So that way we can fully analyze what's going on with the forces, because these forces are connected to the acceleration. So here we're going to draw our free body diagram. Now, here's my car. I'm just drawing it as a box. I know gravity due to the Earth or the planet, whatever it's on, is pointing downwards, the force of gravity. Because it's on the surface, we always exert that normal force, equal and opposite to the force of gravity, because it's not accelerating vertically. Now, I know that the net force horizontally is towards the left, so my force of friction must be acting to the left. Now, so I know that the vertical forces are going to balance out, and so when I add up all the forces in the y, I say they're equal to 0. And if that doesn't make a lot of sense right there, why I said the vertical force is equal to 0, consider asking yourself this. Is this car accelerating vertically? Is it going up or down or anything like that? The answer is no. It's driving straight horizontally on a surface. And so that's how I know that there's no acceleration vertically. And that's why I mathematically set that equal to 0. So now I consider what my positive and negative forces are. So my positive force, because it's upwards, and I guess if you want to be more technical about this, I'm declaring that this is my positive x direction, my negative x direction, and I'm calling upwards my positive y, downwards my negative y direction. So that's sort of the coordinate system that I'm working with here. So this is the coordinate system that I'm working with here. That's why I'm declaring that this normal force is going to be positive. So my normal force, and then the force of gravity points down, so that's a negative force. Minus Fg will be set equal to 0. I can simply add this over. And I'm going to get that the normal force is equal to the force of gravity. And I know the force of gravity is equal to mg. Always. So we're going to use this in just a moment. Now, the important piece of information is with my horizontal information, because I ask myself, is this car accelerating horizontally? The answer is yes. The acceleration points opposite to the direction of motion because it's slowing down. So because there is an acceleration present, I set it to max. And the ax is just consistent with the fact that all of my pieces of information are in the horizontal direction. Now, so let's add up all the forces. In this case, I only have a single force, the force of friction. So we're going to say that negative force of friction equals max. And again, this force of friction is negative because it's pointing towards the left, so therefore it's a negative force. I know that the equation for the force of friction is the coefficient of static friction times their normal force. Well, I already know from the vertical pieces of information that the normal force is equal to the mg. So I can write negative μs times mg equals to max. Doing this is going to cause my m's to cancel out. And as a result, I'm going to get that the horizontal acceleration is equal to negative μs g. And this is a piece of information that's going to be useful to me in just a moment. So now let's consider the information that we have. I have the final velocity to be 0. I have the initial speed to be v, and I now have the acceleration to be minus coefficient of static friction times gravity. And my main goal is still to solve for this delta x min. So I need to think about an equation that involves final speeds, initial speeds, acceleration, and some horizontal distance or displacement. And there's one kinematic equation that can do that for us. It looks like this. The final velocity squared equals to the initial velocity squared plus 2 times the horizontal acceleration times the horizontal displacement. And so this is perfect. I need to solve for my delta x there. But just to make our life simpler, I already know that the final velocity is going to be 0. So I can zero that out already. So this is going to become vxi squared plus 2ax delta x. I'm just going to subtract the 2ax delta x to the other side. It's going to cancel that, cancel that. So I'm going to get minus 2ax delta x equals to vxi squared. And I'm lastly going to divide by minus 2ax. It's going to cancel these out. Minus 2ax. So my final expression for this delta x min is going to be the initial velocity squared, or the initial speed, divided by minus 2ax. So the initial speed is v, so that's going to be v squared, divided by negative 2 multiplied by ax, but ax is negative mu s times g. I'm going to go ahead and get this negative to become positive. And I guess I'll do my work right here. I'll get a final expression of delta x min equals to, on the top, v squared divided by plus plus, so 2 mu s g. So there I'm able to show that the minimum stopping distance is v squared over 2 mu s g. So here we combined a few different ideas about Newton's laws and kinematics together in order to show that this formula was true. Now let's go ahead and try a bonus question. The question is, how would this minimum distance change if we were on the moon instead of the Earth? Well, it's just a really quick modification, but we begin by establishing that the acceleration g, the acceleration due to gravity on the moon, is approximately 1/6 of the acceleration due to gravity on the Earth. All we have to do is, if we're going to find out what that minimum stopping distance is on the moon, then we have to plug in 1/6 out of the Earth. So here I have my minimum distance. But instead of writing just g, because this would represent g on the Earth, I'm going to substitute it with g of the moon. But I can equally substitute that with 1/6 of g. 1/6 of that of the Earth's acceleration due to gravity. So as you can see, when we substitute that 1/6 g, we get that the equation is modified by a factor of 1/6 on the denominator. So let's show the algebra here. V squared over 2 mu s g, but on the bottom it's multiplied by 1/6. I could easily fix that fraction down here by multiplying by its reciprocal, 6/1, to cancel this out. And so the 6 belongs to the numerator, the 1 belongs to the denominator. The minimum distance is 6 times that of what we have on Earth. So we can rewrite the 6 to be on the outside to show that this is the normal stopping distance on Earth. And now we have this factor of 6 in the numerator, which tells us that the stopping distance is 6 times greater, or increased by a factor of 6. So if you're on the moon in the exact same conditions, where the only thing that changes is your acceleration due to gravity, then you're going to need 6 times that physical distance in order for your car to come to a stop just by using the friction alone. And that's going to wrap up this problem on the minimum stopping distance. I appreciate you being here, and I will see you in the next video.